help me, I want to go through the proof of the cosine sum and difference formulas, okay? And once we get the sum formula, it's really easy to find the difference formula. And then I want to go through some examples. Now, what I think is going to happen today, just going through what we did last class, there's going to be some information here that maybe you need to go back and rewatch the video a second time, a third time, a fourth time, to make sure that you're fully understanding what we're doing here, okay? Because when we start to get some examples, there are some nice tricks that we can, I don't even call them tricks, but there's nice things that we can do to guarantee that what we've done and found as an answer is true, is accurate, okay? But if you don't understand kind of the whole dynamics and the interweaving of the trigonometry and what we're really doing, it's almost impossible to recognize the existence of a check, okay? So I think watching the video a couple times, if it doesn't sink in right away in class, it'd be of benefit to you, okay? Okay, so what I want to do, like I said, I want to take the cosine, just kind of give you a reminder of what we did on Friday. We said on Friday, we just learned these rules. We said the cosine of s plus t was the same thing as cosine of s, cosine of t, minus sine s, sine t, right? And what was nice about that is the s plus t was an angle that we were unfamiliar with. It was like a 75 degrees. Well, then we could break that up to 30 plus 45, and even though the right-hand side is expanded, it's much more difficult and complex looking than cosine of 75 does. But what's nice about the right-hand side is that we can then evaluate the cosine of 30. We can evaluate the sine of 30. We can evaluate the cosine of 45 and the sine of 45. Does that make sense? So that's kind of the payoff. Even though it expands and gets a little bit messier on the right-hand side, those components on the right-hand side are much more friendly to us in regards to evaluation than what the left-hand side of cosine of 75 would be. So I want to go through and I want to prove why this exists in this manner. Okay. First thing we're going to do is to talk about this inside the unit circle. Okay. So we got the unit circle here. So if this is the unit circle, point P, we're going to go through and rename some of these things. Point P, we would just call 1, 0, right? Or P sub 0 is 1, 0. Okay. Now, on the unit circle, we've traced out an arc T. Now, that arc T, guys, is the same. We've been calling like S plus like 75 degrees, right? We've been dealing with maybe radian measurements or whatever. But if we go back to what we've talked about in the unit circle, the T, the arc length, is identical in radians to the angle, right? Okay. So those are analogies. Now, obviously, the angle there is shown in degrees, but we convert that to radians. Those would be the same thing. Now, and that's because S equals theta times R, right? In this case, is 1, so S equals theta. Okay. So arc length is S, and that equals theta there. So when I talk about an arc, I could be talking about it as this angle, a central angle. Is that okay? All right, so in the case, if that's T, maybe it's pi over 4. Maybe it's pi over 3. Maybe it's pi over 6. Maybe it's 14 pi over, I don't know, whatever. Okay? 20. Who cares? Okay? What this ordered pair is right here, every ordered pair on the unit circle is a cosine of its respective angle or arc, comma, the sine of its respective angle or arc, right? Okay? So what if this point here be called, let's call it Q1, it'd be cosine of T, comma, sine of T. Is that all right, everybody? Okay. Now, so that's saying, like, you know, if this T was pi over 4, this point here would be cosine pi over 4, sine pi over 4, right? And we know to further evaluate that. Let's say we're looking at this blue arc S. And let's say this blue arc S is like pi over 3, something like that. Meaning the pi over 3 started there and it's going to finish there. Is that okay with everybody? So we're talking ultimately maybe that angle there. Then wouldn't this, because when we measure an arc or we measure an angle, we always go from standard position, right? So P1 wouldn't P1 be attached to an angle that's S plus T? That makes sense? Okay. S plus T. So then P1's ordered pair, P1's ordered pair would be cosine S plus T, comma sine S plus T. Would you guys agree with that? You don't know what's going on there. All right. We good so far? Okay, so that point there is defined as cosine of S plus T, comma sine S plus T. Let's talk about that angle there, going from P sub 0 that direction to Q sub 0. What would you call the ordered pair for Q sub 0? What's the arc or the angle attached to it? Negative S, right? So isn't the ordered pair the cosine of that angle or arc, comma the sine of that angle or arc? So Q sub 0 would be cosine of negative S, comma sine of negative S. Yeah, a lot of parentheses. Okay. Good, right? All right, now before we go on to anything else, I look at that Q sub 0, and what is different about that than all the other angles up there? And it's negative, right? We don't like negative angles, okay? We don't want to deal with them. Remember, we had some even-odd properties, okay? Even-odd refers to symmetry across X and Y axes, okay? Odd is obviously that's something that's symmetric with the y-axis followed by then the x-axis. Even is just the y-axis, okay? What that means then, if I want to know this x value, okay, isn't that x value the same as maybe the x value up here if Q0 was reflected across the x-axis? Does that make sense? So isn't the cosine of negative S, isn't that the same thing? Come on. As the cosine of S. That makes sense, everybody? Okay. Okay, so what that would look like then, so if I put, let's do it in green here. So that green arc would just be S, right? Does that make sense? Okay. Using that reflective idea. So this point here, that x coordinate is the same thing as whatever the cosine is of that point. Okay. Can I get rid of that negative S for the sine as well? But how do these y values relate? This one's obviously going to be sine of S. This one is going to be sine of S. But are they identical? If I go from 0, 0 to get to that point, is it the same direction as they go to that one? No. It's the same distance, but different direction, right? So isn't sine and negative S based off of cofunction rules? Becomes negative sine S. Good. And I think that's going to be a very useful property here for us in regards to kind of working out this sum formula for cosine. All right, now that we've got that set up, okay, and that's kind of like a lot of times we call that like analytical geometry, okay, where we're doing some geometry here with undefined values, okay. We don't know what S is, we don't know what T is, but the relationships that we just defined are true no matter what S and no matter what T are, right? So it's true for all values of S and T. And that happens a lot. We need that ability a lot in regards to trigonometric formulas and just in general all formulas. Okay? A lot of our algebra formulas have a geometry concept behind them. Now, the main reason we're doing this is because there is a segment that we want to create from P1 to P0. P1 to P0. Does anybody remember what that segment is called in a circle in which the endpoints are on the circle? That is a chord. Okay? Now that chord has a direct relationship to the arc that is being made by it. Does that make sense? Now the phrase, instead of saying the arc made by chord P1, P0, we refer to it as the subtended arc. Okay? The word we use for that idea. Okay? So the subtended arc here would be, let's highlight this in purple. Our subtended arc for that orange chord would be that arc. Okay? Would you guys agree that there is another arc in another chord here? Not that one. It goes from Q0 to Q1. And let's make that color. Is that all right, everybody? Okay, that's another chord. And let's look at its subtended arc. Come on. Its subtended arc would be that blue one, right? Okay, so let's do me a favor here. Just kind of work with me. Do these two overlap right there? Okay, so T is the same for both of them, right? What's left over for both of them? S. Okay, so what's that telling me about the subtended arcs of those two chords? They're the same. You guys remember from geometry what it says about the chords if their subtended arcs are congruent? The chords are congruent. Okay? So that is the relationship here that we need to prove what we're interested in here. So let me just prove to you. Yeah. What in the world? There we go. All right, so Q1, Q0, that's 1.66. P1, P0, 1.66. So it proves to you that those chords are the same, right? Okay. And if I were to move, I don't know if I can move this point. No, they're all dictated off a slider that I've got hidden, so I can't move it. But if I were to move that point there, further to the left, this point's going to move further this way, and those 1.66 are usually going to be the same. I mean, there'll be different numbers, but they will equate to one another. Okay? So that's the geometry that we need to be able to move a little bit further within this proof. Okay? Without that geometry, we don't have anything, right? We can't do anything. So as we work in other classes, it's very, very important for us to realize that we've got a lot of prerequisite information that we need to maintain, okay, and keep. And that's kind of what I think people struggle with at the next level, going to college classes, is you get to college, you get to Calc 1 in college, you have graduated high school, right? So every Calc 1 professor you take is going to make the assumption you graduated high school, you know Algebra 1, Algebra 2, Algebra 3, Trigonometry, Geometry, at the back of your hands. Okay? Whether that's a good assumption or not, that's what they make. All right? So you'll be in class talking about a bunch of things that maybe you don't recall at all. All right, and that's fine. That's going to happen. But then, how do you respond to that? Do you just say, "Oh, well, okay, I don't remember this, so I don't need to know it," or "I don't remember this. I need to go back to my high school math and brush up on that stuff." Okay, so that I can follow along in class and continue with discussions and so forth. Okay. So if that's the case, if these two arcs are the same, therefore the chords are the same, doesn't it make sense that P0 to P1 should equal Q0 to Q1, right? That's the idea of the arcs being congruent. So the chords are congruent. These are the chords. So now, if we remember back to the first couple days of college algebra or the first couple days of geometry, we talked about this thing. I'm going to write it this way. You guys remember what this is called? That's the distance formula, okay? Which is ultimately just a Pythagorean theorem, right? Okay? But it's delta x squared plus delta y squared. That's the change in x squared plus the change in y squared, okay? So let's find P0, P1. Let's find that distance for P0 to P1. So what we're going to do is we're going to start with P1 here. I'm going to go cosine. Now I apologize for this, but there's no avoiding it. I'm going to probably run out of room at some point. Okay, so let me come up here and write. So we're going to try to find P0 to P1 equals Q0 to Q1. So P0, so let's start at, we're going to cosine of S plus T minus cosine, not cosine, minus 1. Okay, so it's taking, so we're trying to find this orange distance. So we take that x coordinate minus that x coordinate, correct? And then we're going to square that. Okay, now we're going to add to it the difference in that y coordinate and that y coordinate. So that's a nice one because it just becomes sine of S plus T squared, right? Now the distance for P0 to P1 would be that, correct? Okay, so I got P0 to P1. I'm going to do the same thing for Q0 to Q1. So Q0 to Q1. So let's go cosine T. Let's use that one there minus that x value there, right? So cosine of T minus cosine of F. We'll square that, so that's the difference in the x's there. Plus then, now we'll do the difference in the y. So that y and that y. So we'll go sine of T minus negative sine of S, right? Well, minus and negative becomes positive. So sine of S. And we'll square that. All right, so that's the equation that says P sub 0 to P1 is equal to Q sub 0 to Q1, right? Those two things are equal. Is the left-hand side completely under a radical? Is the right-hand side completely underneath the radical? That means this is a one-to-one relationship, meaning if those are both square rooted on the left-hand side and right-hand side, then doesn't it mean for those two things to be equal, doesn't it mean the radicands have to be equal? Okay. So for instance, here's kind of the analogy I'm trying to make. If this was radical x and this was radical 16, doesn't x have to be 16? That makes sense? Okay, just the radicand here has to equal that radicand there. So the idea holds here. So what I can really do, even though I'm doing distance, you can just kind of pull those things out. Just look at the radicand. If you wanted to square both sides, that's going to work too. It's going to get the same thing. But now we've got that. Now, what we're going to do is the algebra here. So I'm actually going to get rid of, I'm just going to move off that circle there so I got a little bit more room here. Let's go through the algebra. We've got a bunch of things up here being squared, right? This is a difference being squared. It's a binomial being squared. So when I do this, I'm going to have cosine squared of s plus t, right? So that's square the first part. Now multiply these two things together, and you get negative cosine s plus t, and then you're going to double that. So you get negative 2 cosine of s plus t, right? And I take my negative 1 and square that, so I get plus 1. Is everybody okay with what just happened there? That's using the a plus b squared rule turns into a squared plus 2ab plus b squared. Okay? Just kind of expanded that. Now, we're going to do the same thing over here, but this is just a monomial squared, so this thing just stays as plus sine squared of s plus t. So it's expanding the left-hand side. Let's expand the right-hand side. Again, you have binomial squared here. So it's going to turn into cosine squared t. Now you're going to multiply those together and double, right? So it becomes negative 2 cosine t cosine s. And then you're going to square the last term. So it becomes plus cosine squared s. And now here, you got to do the same thing, but now it's with sine. So it'll be sine squared t. Multiply together and double, so plus 2 sine t sine s. And then square the last part, so it becomes plus sine squared s. Now, it's ugly looking. It was a lot of expansion there. But if you think about it, the only expansion we did was square first term, square last term, multiply terms together, and double them, right? Okay. So it's just like taking x minus 3 squared and expanding that. Or, maybe cosine of x minus 2 and it's squaring that and expanding that. So all algebra, I think that we have the ability to do. Now, what happens there, even though that got ugly, some real nice things just occurred. And hopefully you're seeing them as we were working through. And the first one that we see that's real nice is that thing right there. What's that turn into? That's 1. Okay? So I'm going to rewrite this as negative 2 cosine s plus t. Now what I highlighted turns into 1, but there's a plus 1 out there as well, so it's going to be plus 2 on the left-hand side. The right-hand side, we should have some similar things occurring. We have a cosine squared t. We have a plus sine squared t. What's that turn into? That's 1 as well, right? We also have a cosine squared s and a sine squared s. What's that turn into? 1 as well. So coupled with the other one, that's a total of 2. So on the right-hand side, we've got 2 minus then 2 cosine t cosine s plus 2 sine t sine s. All right, so it's a little bit easier looking. What happens with these 2's? They cancel out, right? Now think about what we're trying to get to. We're trying to isolate cosine s plus c. We're trying to do the cosine sum formula. So what do I need to do in order to get cosine of s plus t isolated? Divide by -2, right? If I divide the left-hand side by -2, the right-hand side with those 2's wiped away looks like this. Divide that by -2, so it gives me cosine of t, cosine of s. Now this becomes minus sine of t, sine of s. And using the commutative property of multiplication, we can rewrite cosine of s plus t equal to cosine s, cosine t. We can flip-flop these two, right? Minus then sine s times sine t. And that is exactly the sum formula for cosine we talked about on Friday, right? And that is, hopefully you see, because of the division by the -2, is why the signs change, SIGN, changes from the left-hand side of the condensed cosine s plus t to the expanded side, cosine s, cosine t, minus sine s, sine t. Okay? Now, that's just the sum formula. Finding the difference formula is, with that picture, probably something we could do. But it's so much easier if we make an algebraic statement here. Would you guys agree that if I wanted to go cosine of s minus t, is that the same thing as cosine of s plus the opposite of t? Okay? And that relationship right there, the fact that adding the opposite is exactly the same thing as subtracting, is actually a tool that you'll use a lot in proving all types of algebraic properties and relationships later on in other math classes. But now let's go through and make that substitution into this. We have cosine of s, but now it's cosine of negative t, right? Minus then sine of s times sine of negative t. All right? So that's cosine of s. Now cosine of negative t, don't we have that even odd property that the cosine of a negative angle is the same thing as the cosine of the positive angle? So it just turns into cosine t. Minus sine of s. Now this thing here, the sine of a negative angle, we know the sine of negative theta is equal to negative sine of theta, right? So that thing turns into minus sine of t, or the opposite of sine of t. And now I got a negative times a negative. What's that turn into? Positive. So that's plus sine s, sine t. And that's the reason then when I start with the minus there, a difference in the cosine, it turns into a sum in the expanded side of the formula. Okay? And that, I think I even maybe have, in regards to the amount of work, maybe one line that's kind of maybe not necessary. I don't think that second line is necessary there. I think we can rewrite sine of negative t as the opposite sine of t and multiply it by the negative out front of the sine of s all at once. Okay? So hopefully you see the proof of cosine of s minus t much simpler if we use that property that adding the opposite is identical to subtraction. Okay. Tomorrow, I think we'll go through and do the sine sum and difference. And once we have that, maybe try to look at why the tangent's the way it is. Okay. I want to do some examples today that you're seeing in your homework. Okay, so the first one, we did example 2 Friday, the cosine 14, cosine 46, right? We got that to cosine 60. What I want you guys to understand is that there's not directions that tell you to keep going until, this one actually does. It says, and I think I wrote it this way last year for this purpose. It says, as a trigonometric function of one number, okay? Meaning basically go as far as you possibly can. Okay? So as you're working in your homework or testing quizzes, if you simplify something, you get cosine of 60, don't stop there. Can't you evaluate cosine of 60? You know that it's 1/2, right? So keep going further until you have exhausted all substitutions, all evaluations. It would be really nice if at the end it told, or in the directions, it told you, hey, your answer should look like something like this, but it never does that, okay? Through the rest of the math class that you ever take, you're really never going to have something like that kind of in mind as you're starting a problem, okay? Now, after doing a couple that are similar to one another, you might have an idea of what that final outcome should look like, but in general, we don't, okay? So just keep going until you've evaluated everything. So a lot of times on test quiz, I'll get somebody to write cosine of 60 as the answer. Yeah, but you can go further, okay? That's like saying 2/4 is the answer. Yeah, but can I go 1/2? Or some of you had on the test the other day, you had 2 over radical 3. Yeah, but can I regret that 2 radical 3 over 3? Okay? So those are the kind of things to think about as we're moving through. All right, we've done this, okay? We have worked with this idea with right triangles. Okay, so if this is, let's just say if this is u here, doesn't this have to be 90 minus u? Okay, and if I look at the cosine of u, so let's call this x, y, and r. If I look at the cosine of u, actually let's do the cosine of 90 minus u, so it's identical to what we got up here. Cosine of 90 minus u, isn't that y over r? Okay, and if I go then the sine of u, isn't that equal to y over r? And if those two things are equal, what does it say about those two things? They're equal. Okay, so we've done that with right triangles. We've done this thing with transformations. We've graphed the cosine of pi over 2 minus u, and we've graphed the sine of u, and we've seen with transformations that they are just phase shifts from one another. Does that make sense? Okay. And actually, if I graph those both together, they overlap each other. But we've talked about how we could take the sine function and translate it left or right, and it becomes the cosine, right? Or we take the cosine function, translate it left or right, and it becomes the sine. So we've done that. This is asking us to prove it a different way. This is to prove it using the sum and difference formulas. And this, I think, is actually the easiest way of proving these, okay, or this relationship. Because if I know my sum and difference formula, I know that cosine, let's just say of alpha minus beta, I'm just going to write my rule here, that is equal to cosine alpha, cosine beta, plus sine alpha, sine beta, right? That's what we've talked about in the past. I mean, using alpha, beta, S or T, or whatever you want to use as your variables. Well, now I've got a case. Now I've got alpha to be pi over 2 and beta to be u. Well, that means all I've got to do is take this rule. Wherever I see an alpha, I replace it with pi over 2, right? Wherever I saw beta, I'm going to replace it with u. So this becomes cosine of pi over 2, cosine u, plus sine pi over 2 times sine of u. All right. Now evaluate. Because now you've got some substitutions that can be made, right? Do you know the cosine of pi over 2? What's the cosine of pi over 2? 0. It's because 0. I don't know cosine of u because I don't know what u is, right? What's the sine of pi over 2? 1. But I don't know what sine of u is because I don't know what u is. But I can start doing a little bit of work here. What's this algebra going to tell me that goes to? 0. This algebra here turns that into sine of u. What's 0 plus sine of u? Just sine u. Did we start with cosine of pi over 2 minus u? Did we get to sine of u? So we've proven it. Okay? You're going to see one of those on your next test. Okay? Now, we can do it with sine. Pi over 2 minus u is equal to cosine u, that kind of thing. We do it tangent, cosecant, cotangent, all that kind of stuff. So, okay, the next one. This for some reason is a question that trips people up all the time. You're going to see it on this test. You're going to see it on the final. We just need to cover this in great detail. This is the one I was talking about at the beginning of class that said there's a really nice, convenient check for this if you understand what's going on. Okay? It says cosine of theta minus phi. That second symbol there is the Greek letter phi. If you don't like the Greek letters, don't want to use them, fine. Go x minus y. It doesn't matter. Okay? But we usually use, like I said in the past, we use those Greek letters to represent angles. It says cosine theta is 8/17. Theta is in quadrant 4. Tangent phi is negative radical 15. Phi is in quadrant 2. The quadrants tell us something about the signs, okay? So the plus and minus of things. So that's very important. Those are not just there to be there. We need those, okay? What they're telling us is to evaluate that. Figure out what cosine of theta minus phi is. Well, we know that cosine of theta minus phi looks like this. Cosine theta, cosine phi, plus sine theta, sine phi. Okay? We are certain that is true, right? In order to evaluate this and figure this out, I need to be able to substitute that, and that. Is that okay with everybody? Now, one of those you know from the given information. And a lot of times with these questions, you actually know two of those things. This one's kind of different because they give me tangent instead. But don't I know cosine theta? I know cosine theta is 8/17. So I could go in right now, and where I see cosine theta, I'm going to rewrite that as 8/17. But now I need to multiply that by cosine phi. Well, I don't know what cosine phi is. I need to add to a sine theta, sine phi. I don't know what either of those are. Okay? But they give me enough information here and here to determine those. Okay? So, what we have to do is draw a picture every single time. And we'll draw a picture to figure out what theta is. Theta is cosine theta is 8/17. Theta is in quadrant 4. So maybe that's theta. That's my angle theta. In quadrant 4, then, doesn't there exist this right triangle? If they're giving me cosine of 8/17, doesn't it give me that information right there? Now, with the Pythagorean theorem, this is 289. This is 64. Subtract those. 225. Square root of 225? 15. Okay? Now, with that triangle, no matter what quadrant that triangle is in, if I've got cosine is 8/17, I'm always going to get 15, right? For that missing value. But why do they tell me it's got to be in the fourth quadrant? So that I know it's negative. Okay? Because now I come up here. I still don't know cosine phi. Phi yet. But now I know sine of theta. What's the sine of theta? Negative 15 over 8. Oh, sorry, negative 15 over 17. Okay? Negative 15 over 17. Opposite of our hypotenuse, right? Does that make sense? Now let's go through the same exact process, but do it with phi. Says it's in the second quadrant, right? So this blue arc here, blue angle would be phi. Says tangent. Tangent, we want to view this as a ratio, right? So it's negative root 15 over 1. So opposite of adjacent, so it's got to be root 15. And that's got to be 1, right? Which one of those is negative to make this negative? Is it the root 15 or is it the 1? The 1. Okay, so now, just like we did over here, the Pythagorean theorem is going to tell me negative 1 squared is 1. Radical 15 squared is 15. Add those together. 16, and that will be 4, right? Okay. Now, and that's positive, right? The radius is always positive. Okay. Do I know the cosine of phi now? Cosine of phi is going to come from this triangle here, right? Negative 1/4. Do you know the sine of phi? Root 15 over 4. They give me negative 8 over 68 minus 15 root 15 over 68. If you want to condense that to one fraction, I got that. Okay. Is that something we've kind of already done before? We've done that stuff with the triangles in the bottom left before, right? Okay, now we haven't done it twice in the same problem, but now we can. I want to go through, we got 5 or 6 minutes here, so bear with me if we run out of time. We should be right up to the bell. We're going through a check for this, okay? If you know, so I don't know what phi and theta were, right? But I do know that cosine of theta is 8/17. I know tangent of phi is negative root 15. And because I know how cosine and arc cosine work together, shouldn't knowing cosine of theta being 8/17, shouldn't I be able to take the arc cosine of 8/17 to find out that angle of theta? Does that make sense to everybody? So let's do that, okay? I'm just going to do this in Desmos real quick, just because it lets me cut and paste a little bit easier. I'm trying to get rid of that red bubble that was there. All right, so I'm going to go arc cosine of 8/17. Okay, I think it's best to do, it's just going to make our subtraction and stuff here in a moment easier if we're in degrees. So 62-ish degrees, right? But it says we're in what quadrant? 4th quadrant. Okay? So if I'm in the 4th quadrant, what we're really dealing with, if we remember what the arc cosine is only going to give you something back between 0 and pi, right? Okay? It just gave us back this angle here to be 61 degrees or 62 degrees. Okay? If it's in the 4th quadrant, that means with reflections, that would be negative 62 degrees, right? That is theta, though, that we're interested in. So should I be able to take 360 minus, and that's the angle that I'm actually talking about for theta? Okay? Now I'm just going to make sure that makes sense. If I go cosine of that angle, and this is the nice thing of understanding what our cosine functions and our arc cosine functions are all about, it gives me that right there, which is that the same thing as 8/17? Yes. Okay? So I'm good. That's theta. Now phi. Phi, they said, was negative square root of 15, right? Okay. Now if you know the arctangent function, it's only going to give you back information between negative pi over 2 and pi over 2. Well, it just gave me back this angle here to be negative 75 degrees. I'm going to use a little bit of geometry here. But if I were to extend that ray, what's that angle right there going to be? 75 degrees. Okay? So now phi, which is actually there, okay, that would be 180 minus the 75 degrees, right? So I got to put another negative in here to negate that 75 degrees. So there's phi. All right, everybody? So the cosine of theta minus phi should be that number there. Does that make sense, everybody? Okay. So if cosine of theta minus phi is that thing right there, but we found it to be -8 minus 15 square root of 15 all over, was all over 68? Are those two numbers the same? Yeah. Okay. Now, I'm not just getting those numbers by happenstance, right? I mean, I've done some work there. We've done some work there to prove that what we have accomplished with that -8 minus 15 root 15 or 68 is the exact answer, okay, for cosine 98.072 minus 104.477, okay? So that's kind of a task that you can now, obviously, that check took 5 minutes, okay? So if I'm on a test or quiz and there's 2 of these or something like that, I'm running out of time, maybe that check isn't going to be available to me. But if I've got time, because somebody had time the other day on that test to go back and check some things, okay? So that might be something to think about. Also, I think doing your homework, if you can go through that check, it's going to reemphasize ideas and concepts to you. It's going to make this class a whole lot easier if you can do those types of things, okay? 7-2 is still open. Keep working on that. Tomorrow, we'll talk about the sine, sum and difference formulas, and the tangent, sum and difference formulas. And then hopefully about halfway through class tomorrow, I'll move on to 7-3, which I believe 7-3 is talking about double angles. Yep, double angles and half angles. So we'll start there, like sine of s plus s. We already know what that should look like. Well, that's the same thing as saying s of, or sine of 2s, right? So we'll be able to maybe make some relationships there, double angles.